we're going to do a little practice and kind of put things together graphically. Okay, so just a sum up of kind of different scenarios. Conditions on the derivative. So if the first derivative at a point A is positive and the second derivative is also positive, if we know the first derivative is positive, that tells us the function is increasing. If the second derivative is positive, that tells us the graph is concave up. So that would be something like this sort of scenario at this point A that we're talking about. If the first derivative is positive, but the second derivative is negative, then we are increasing, but we're concave down. So it's going to look something like this. If the first derivative is negative, that means the function is decreasing. If the second derivative is positive, it's concave up. So that would be something like this. And if the first derivative is negative and the second derivative is negative, then we are decreasing and concave down. So those should hopefully all make sense. That's just kind of summing up a lot of the stuff we've been talking about in 9.3. Here are other ways to think about it. So the first derivative, positive, that means the curve's rising or increasing. If it's negative, that means the curve is falling. If the first derivative is 0 or it does not exist, that is a possible local maximum and minimum. Local maximum or minimum. That's what we call a critical value. For the second derivative, if the second derivative is positive, the curve is concave up. If the second derivative is negative, the curve is concave down. If the second derivative is 0 or does not exist, that is a possible point of inflection, or a point where concavity changes. That's what an inflection point is. So what does f of x, f prime of x, and f double prime of x tell us about a function? Well, I mean, we've been dealing with functions, since you did Algebra 1. So, and what does it tell you? Well, it tells you where things are on a graph. So this is going to give us the where. And by the where, I mean, if I plug in a value for x, I get a y value. So that gives me a location, right? But if I have the first derivative, what does that tell me about the original function? It tells me about the slope on the graph. So if the first derivative, I plug in x, or a value for x, and it's positive, then I know that the function has a positive slope. It's increasing. If it's negative, it has a negative slope, so it's decreasing. And then the second derivative, this is what we just talked about recently, and this tells us concavity. So it's going to tell us the shape of the actual curve. Is it concave up or is it concave down? Let's look at this with an example where we have the derivative of the function and the second derivative graphs. So looking at the graph of f prime, which is the red curve, and f double prime, which is the green curve, and we're looking when x is close to 10. So why does f of x have a relative minimum at x equals 10? So using the first derivative graph and the second derivative graph, I want you to explain why that is. Pause the video, unpause when you're ready to discuss. So using my derivative speak, I'm essentially just doing the second derivative test. So since f prime of 10 equals 0, so I can see that that makes 10 a critical number. I also see that 2 is a critical number. And f double prime of 10 is greater than 0, so it's positive. And remember, I don't care how positive it is, I just care that it's positive. So then at x equals 10 is a relative minimum. Now in this case, I can see that that looks like it's probably the point 10.1. So I could have said at the point 10.1. But since we're only really talking about just the x value here, I just said 10. Now I want you to go ahead and do the next 4 graphs on your own. So on all of these 4 graphs, the solid line is the first derivative, the dashed line is the second derivative, and using what we know from the first derivative and the second derivative, I want you to draw the function. There are many correct answers, keep in mind, okay? But I want you to go ahead and do all 4 of them. Pause the video, unpause when you're ready to check all 4. Okay, so if we look at the first one here, hopefully you have something like this. It's not going to be perfect, all right? But the idea is that you have the key features correct. And that is that when x is 0, the function should have a relative maximum. When x is 2, the function should have a relative minimum. And when x is 1, there should be an inflection point. And then the general shape should be the same. Whatever type of symmetry you have, that part doesn't matter. how high or how low, you know, whatever the y value is of this point does not matter as long as it's above this point. That's all. Otherwise, we don't know anything else. And keep in mind that a vertical shift of a function won't change its derivative. So that's why the y values don't matter. Because if I have a function, if I just do a vertical shift to it, it's not going to change what the derivative is. All right, next one here. I should have something like this. Again, it's not perfect, but I know I should have a relative maximum here when there's a derivative has a 0, a relative maximum here when the derivative has a 0, and also keep in mind that so the derivative has a 0 here, and the second derivative is negative. So that's why I know this is a relative maximum. Same with this. Derivative has a 0, second derivative is negative, so this has to be a relative maximum. Here the derivative is 0, but the second derivative is positive this time, so this has to be a relative minimum. Here the second derivative is 0, and here the second derivative is 0. Those are going to be inflection points. Other things you can think about is concavity. Since the second derivative is negative, I know it has to be concave down from this part. The second derivative is positive from here to here, so that should be concave up. Second derivative is negative here, so this should be concave down. First derivative is positive up until this, so the function should be increasing. Then the first derivative becomes negative, so the function should be decreasing. And then it becomes positive again, so it should be increasing, and then negative, so it's decreasing. Remember, there's a lot of ways in which you can really check to make sure that your shape of the graph is correct. Next one, this is probably a little bit more difficult for some of you maybe. So I only have one critical value from the first derivative, and that's when x is 0, and I see that the second derivative is negative there, so that has to be a relative maximum. I have two possible points of inflection on the second derivative, and since I switch from negative to positive and positive to negative, I know that those are actual inflection points. So now, how do I know what the shape is though? Like, how do I know that it's going to plane off like this? That's a tough thing to think about. But think about, what does the first derivative represent in terms of the function? It represents the slope, right? So notice that the first derivative is approaching what looks like probably a horizontal asymptote of y equals 0. That means the slope is getting really, really close to 0. That means the function is also going to approach what looks like probably a horizontal asymptote of y equals 0. And the same thing over here. The only difference between the left side and the right side is the first derivative was positive over here, which meant that the function was actually increasing. And then over here, the first derivative was negative, but remember, all the negative does is tell us that the function is decreasing. But because the first derivative is getting very close to that horizontal asymptote of y equals 0, the function is really, really planing out and approaching a slope of 0. And then the last one, similar to two examples ago. So first derivative is 0 here, and the second derivative is positive, so this has to be a relative minimum. First derivative is 0 here, second derivative is negative, so that has to be a relative maximum. First derivative is 0 here, and the second derivative is positive, so that has to be a relative minimum. Second derivative has zeros at these 2 points, so those are going to be my inflection points. And because the second derivative changed from positive to negative and negative to positive, I know they are actually inflection points. All right, next one. I want you to try this on your own. As you can see, this is from an AP exam with no calculator. So you're given this table about information about a function, its derivative, and its second derivative on these intervals and at these points. So we're going to say let f be a function that is continuous on the interval 0 to 4. So we're only thinking about this from 0 to 4. The function f is twice differentiable except at x equals 2. That means the second derivative exists everywhere except for at x equals 2. The function f and its derivative have the properties indicated in the table above, where d and e indicates that the derivative of f does not exist at x equals 2. So for the interval 0 to 4, I want you to find all values of x at which f has a relative extremum. Determine whether f has a relative maximum or relative minimum at each of these values, and justify your answer. So pause the video, do that, unpause when you're ready to check. Here we just have one relative maximum, and that's going to be when x is 2, and then the y value conveniently is also 2. So we can say since f prime of x is greater than 0 on 1 to 2, and f prime of x is less than 0 on 2 to 3, at 2, 2 is a relative max. What else we are going to look for is, okay, so at 1, there was a critical number, but the signs didn't change, and the second derivative test failed as well. So that's not a relative min or max. At -3, signs didn't change. I'm sorry, at +3, I take that back. We didn't even have a critical number. I just misread that myself because we got -3. So we didn't even have the only possible critical numbers were at 1 and at 2, where the derivative equal to 0 or does not exist, and the only one that had a sign change was at 2. So that's why we just have a relative max. Now I want you to actually try and sketch the graph of this function. So pause the video, do that, unpause when you're ready to check. So it could look something like this. Because I do know a lot about the concavity. I know it starts out concave down, but it's increasing. Then it becomes concave up. So there is an inflection point there at 0, at the point 1, 0. And then at 2, at this relative max, that's going to be a sharp turn. So that's why the derivative does not exist. So my picture might not be perfect, but that's supposed to be a sharp turn. So it's like going up, and then it continues on. And it changes concavity there as well, because it changed from concave up to concave down, and then it changes concavity again at the point 3, 0. So there's another inflection point here, and then I just know that it's concave up. I don't really know, and that it's decreasing, but I don't know how far it's going down. Last one, I want you to try this on your own again. So water's running into this vase as shown. I want you to sketch a graph of the depth of the water in the vase as a function of time. So you're assuming that water is being poured in there at a constant rate. So the water filling it is a constant rate, but the depth of the water is going to change over time because of the shape of the vase. So I want you to try to draw a sketch of that, so try to visualize that, and then answer the questions, does the function have any extrema, explain, and then interpret the inflection points of the graph. Pause the video, do that, unpause when you're ready to check. Again, this is not perfect, but our graph should have something like this kind of shape. And so we have these two inflection points, and those occur. So here's our first inflection point, where the water is increasing, but it's increasing at a decreasing rate because the vase keeps getting wider and wider and wider. But then once you hit this point, that's that inflection point, now the vase is getting narrower, so the depth is actually going to increase quicker. So now the concavity switches from concave down to concave up until we get to this part of the vase where it's at its narrowest, but then it becomes wider again and we continue to increase. But we switch to concave down. So something along these lines. Again, doesn't have to be perfect, it's just an understanding of what this is going to look like. Then part B, does the function have any relative extrema? No, there's no relative extrema because the first derivative is going to be positive the entire time. The function is always increasing because the water is always flowing in until obviously you'll start to overflow at some point, but it's still not going to empty out. So then part C, interpret the inflection points. So it's the rate of change of D is decreasing until the widest point, and then it's increasing until the narrowest point, and then it's decreasing again until the top. And so that's what's happening here. There's that widest point and there's that narrowest point. Okay, so again, we just want to continue to understand the relationship between a function and its derivatives.